Okay, good morning, BC. I hope you're being good for the sub. This should be Monday, the 25th. I'll be back tomorrow, and I'm going to start with notes on Review 5, which is derivative applications. If you would get that out, please. If at any time you have a question and you want to discuss something, then ask the sub to pause the video and you guys can work it out. And if I'm wrong on something, then you can come to an agreement, and that's fine. It happens. So here we go. Hopefully you're ready. And let's go. Applying a derivative has so many applications. Probably do this another day tomorrow. But let's get started. First of all, we typically find critical numbers. Numbers are in the function where something interesting might, not necessarily has to, but might be happening, like mins, maxes, and so on. All right, get the definition down because most people only remember half of it. A function has a critical number at x equal a if x equal a is in the domain of f and f prime at that point is 0 or undefined, if that's a critical number. It could be a place where the graph goes flat or has a sharp turn, and that flat could be a min, could be a max, or could be a neither. And that sharp turn could be a min or could be a max kind of thing. All right. We will, after finding the critical numbers, go on and test what's happening there with the first or second derivative. We'll cover both those in a minute. Let's start here, though. So if I give you a critical points question, the first thing you should do is find the domain so that later you don't look like a fool and say, hey, there's a critical number at 0 when 0 is not even on the function. So in this case, the domain is x is not 0 and 1. Everything else is cool. I am going to get the old derivative next. Find g prime. And if this is x minus 1 to the negative 1, then I reckon this would be negative 1 x minus 1 to the negative 2, or negative 1 over x minus 1 squared. Same deal here. This would be x to the negative 1. So that's plus 1 over x squared. If you said natural log, obviously you're thinking antiderivative, not derivative, right? Now, if I don't want to know if this is 0 or undefined, then I'm going to need to do more. So I might get something like get a common denominator, x squared, x minus 1 squared. And what do I get here? Negative x squared. And this, when I multiply this fraction top and bottom by x minus 1 squared, it would be plus x squared minus 2x plus 1. I hope I did that right. Check with each other. Say, yeah, he's good, or what a knucklehead. And let's continue on. Assuming I'm correct here, I have negative 2x plus 1 over x squared, x minus 1 squared. My critical numbers, therefore, the derivative is 0 at 1/2. The derivative is undefined at 0 or 1. But 0 and 1 aren't actually points on the original function. So my critical number is x equals 1/2. All right. That's a reminder. Hopefully that's coming back to you. Let's go on to the next idea. How was your weekend, by the way? Oh, good. All right. Cool. The extreme value theorem. The extreme value theorem, or EVT, is all about absolute extrema, like champion of the world. Sometimes you'll hear absolute extrema referred to as global extrema, and relative extrema is local. Well, we're talking not the champion of your neighborhood, local extrema. We're talking champion of the world, global extrema. Greatest possible or least possible y value. Now, if you think about this, the first part, when do you have to have one? when could you have, when there's a difference between have to and could. If I had an enclosed endpoint and I traveled right to another enclosed endpoint without ever picking up my pencil, I would have to have a point that was lower than all others and higher than all others. Have to. Now, I could have multiples of the same point, like a sinusoid, but I'd have to have at least one of each. Those two components are the key. If you think about has endpoints, and is continuous, then you get some different situations. Now, has endpoints alone could be discontinuous, and it might look something like that. Now, that wouldn't have an absolute max because of that infinite behavior, even though it has endpoints. Note that graph would have an absolute min, but not an absolute max. So that's could versus has to. It could have absolute extrema, but doesn't have to. Continuous could look like this. If I let it go forever, it might look like that. That does not have an absolute minimum because it goes on forever in the negative direction. Notice it does have an absolute max. Could have an absolute max, doesn't have to. You could also just say, hey, here's a line that goes forever up. That has no absolute min or max. So that's a case of none, not even could. But if you look at the combination of those two, continuous with endpoints, no matter what you do, that intersection must have absolute min and max. This is could have. This is could have, but not must have, all right? So the idea of the extreme value theorem part one is if a function is continuous on a closed interval, it must have absolute min and max. All right. The second part is where those are. Well, that graph also, that Venn diagram also shows that. Part two is absolute extrema must be special. Absolute extrema must, actually, I'm going to say only at. Must is good, but only at either a critical point. I'll say critical point or critical number interchangeably. Either one's fine. Or an endpoint. So when you go looking for absolute extrema, you're really only looking at some candidates. And because of that, when you do absolute extrema, you're going to do a candidates test. This is how I'm sure Mr. Otterstetter taught it. This is how I teach it. This is how AP expects your work to look. It's just good math, okay? It's not my thing, all right? How you structure your table and stuff, that's not important to me. It's just that you look at all those candidates. So let me walk you through how I would do this, and hopefully your work looks something like. Find the min and max of g of x on 0 to 2. It says the min, not a min, the min. Now that word, that's pretty strong. That small little article actually means you're looking for absolute extrema, not relative, absolute. And so right away, this might be different here. I require you to cite the EVT. Now, this is not universal. To me, it's important. It's like the thesis for the argument. It tells the reader, hey, I'm going in this direction. Absolute extrema only at endpoints or critical numbers. Feel free to abbreviate, but I require that. Now we're going to go, we have the endpoints, they're given, as they often are. The critical numbers, we need to gather those. I know the domain already, so I'm not going to do the domain here. The domain, the root is never going to have a negative anyway, so there's no issue there. And 0 to 2 is a domain. So I'm going to ignore the domain step, just have 0 to 2 in my mind as I find the critical numbers. G prime. By chain rule, hopefully your technique skills are good. So when I have the derivative of x squared plus 1 to the half, I'll take the half down. It becomes x squared plus 1 to the negative 1/2. But then by chain rule, derivative of the inside is the derivative of x squared plus 1 is 2x. Then minus x's derivative is minus 1. The critical numbers are where this is 0 or undefined, so I'm going to say that. Undefined doesn't look like it's going to be an issue because although I do have a denominator, it's never going to be 0. Root x squared plus 1 is always 1 or more, so that's not going to be an issue. If I do a little more here, I'm going to get a common denominator. So the common denominator is root x squared plus 1. 2x in the first fraction stays the same, and the second becomes minus x squared plus 1 square rooted is 0 or undefined. I should maybe have that on the right. It doesn't matter. Goodness, so this is getting ugly, but it is what it is. Remember, g prime is undefined if x squared plus 1 is 0, but that's not happening. So g prime is 0 if the numerator is 0. That's if 2x minus root x squared plus 1 is 0. Good thing you guys know so much algebra. You can solve that well, I hope. And I get something like 3x squared equals 1, x squared equals 1/3, x is plus or minus the square root of 1/3, but because of the domain, it's just plus. That's the only critical number in the domain, all right? So my critical number is the square root of 1/3. Now, I have three things that are interesting, and going from 0 to root 1/3 to 2. Root 1/3 is a place where the graph is flat. I don't know how these two compare, which one's higher, which one's lower. I don't know if root 1/3 is higher or lower. So I have these 3 points, and I don't know, what's going on at each of those. Well, I need to find the y values and compare to see, which of the candidates has the greatest value and the least value. I structure my table this way. That doesn't have to be the way you do it, but I'm looking at the y values for each of the 3 candidates: 0, root 1/3, and 2. I'm plugging into g. I want y values on the original function, not the derivative. And here I go. If I plug 0 into the original function, I get 2, I believe. If I did that right, check me on that. Root 1/3, well, this is yuck. So what do I got there? 2 root 4/3 minus root 1/3. That's, I guess, going to require a little more work. Sorry. I'm looking at that and getting scared, but I shouldn't be. The square root of 4 is 2, so this is 4 over root 3 minus 1 over root 3, so it's 3 over root 3. Not pretty, but neither am I, so what are you going to do? All right, so what about 2? 2, if I put in 2, please be clean. Nope, not clean. 2 root 5 minus 2, or 2 times root 5 minus 1. Oh, doctor. So isn't this just root 3? Am I wrong in thinking this is root 3? You probably are already picking up your calculator because you're a weasel, but I'm thinking this is like 1.8-ish, if I recall. This is 2 point, maybe something-ish, 2.3, 2.2, so this is 2 times 1.3, it's maybe 2.6-ish. So I'm feeling that's greater. I could also do a sign test. around root 1/3 to see if it's going up after that or down. That would also have been smart, but that's not me. So anyway, I know enough to make a conclusion. This is the greatest value. Pretty sure. And yeah, I'm confident there. And this is the least value. So my conclusion is, now pay attention to, is it where is the absolute min or max, or what is the absolute min or max? The absolute min is the square root of 3. The absolute max is 2 root 5 minus 2. And hope that's right. Anywho, good stuff. That's your conclusion. Some people add on to this and say because it's the greatest of the candidates, or because root 3 is less than 2, which is less than 2 root 5 minus 2. If you have been taught to do that, you should keep doing it. This is really lovely work. I wasn't taught to do it that way. It's just not my habit, and I'm an underachiever like that. So I don't require it, right? So let's go to the next one. Find the min and max values of this. Now, what makes this one a harder one, this is AP, College Board doesn't usually go with this problem. It's hard. And usually you got to keep in mind that they need to make a test that can be graded on a large scale quickly. And so always have that in the back of your mind. A college professor often would go in this direction because it's a good problem. This is a could case. It doesn't have endpoints, so it doesn't have to have min and max, but it could. In order to get there, I'm going to start with the EBT. It's still an absolute max problem, so absolute min and max doesn't, the first part isn't satisfied. It doesn't have to, but if it does, they still have to be at endpoints or critical numbers. There are no endpoints, and so I just have to look for critical numbers. The domain is all reals because x squared plus 1 is never 0. F prime is x squared plus 1 to the negative 2, so x squared plus 1. And then the derivative of the inside is 2x. This is 0 or undefined at x equals 0. Now, normally I do a candidates test, and some teachers, maybe your teacher, I don't know, might do something like this. I don't really, I guess I see where you're coming from. I like that, but I like better just kind of going in a, let me get more information from a sign test. The derivative goes negative forever up to 0 and positive forever after, which means that I did this derivative wrong. It was x squared plus 1 to the negative 1, and the derivative is negative 2x over x squared plus 1. Sorry about that. And so that means the derivative is positive and changing to negative. I knew that because this is a really famous, fun story in math. This graph is called The Witch of Agnesi. It comes from a translation error into the Italian. But at any rate, it's a kind of precursor to the bell curve. It's not the bell curve, but anyway, I know it should look like that. And the sign test tells me that the derivative is always positive, then always negative, and therefore the function is always increasing, then always decreasing. I have to have an absolute max there. Now, the wording is the hard part. Pay attention. You word it strongly with really harsh math language, and I'm talking only or forever. That's kind of math strong language. If you say that in math, you go, oh. So it's something like this. The function f has an absolute max. Does it say where it is or what it is. It says find the min and max values of the values. So I want the value. I need not at x equals 0, but what is it? The greatest possible value of the function has an absolute max value of 1. Now, if you want to parenthetically say at x equals 0, cool. I don't have to. Now I'm going to justify why here. And that's because x equals 0 is the only critical number. That kind of covers your tush so that nobody can say, well, maybe it turns up later. And the derivative is positive for all x less than 0, and f prime is negative for all x greater than 0. A layman would probably prefer, the function is increasing all the way up to 0 and decreasing ever after, but a calculus person cites the derivative, not the function, right? A lot of words there. That's a hard case. A parabola is very frequently just a general case. You do an absolute extreme problem on a parabola. Okay. I need to pick it up here. Now I'm going to just write you a quick note or two, just to remind you. First derivative, increasing means f prime, or whatever the derivative might be, is positive. Decreasing as f prime is negative. I am writing either one. You can do both in my class. You can use symbols to say positive. You can use words to say negative, positive. You may abbreviate on a homework and probably on the test, honestly. But on the AP, we're going to do better. On horizontal, now it's hard. No, I take it back. Horizontal tangents is either when the derivative or dy dx is 0. Now, if it's a fraction, then you're talking the top, or the numerator in actual math language, is 0. Vertical tangents, things do have vertical tangents. For example, the cube root function, which that's a classic example, looks like that. It has a vertical tangent at x equals 0. At any rate, whether the derivative or dy dx is undefined, which is to say the denominator is 0. Now I want you to, when you get to the homework, you're going to have some stinkers. Sometimes dy dx, if it wasn't a function, like a circle or something, then dy dx might be a function of both x and y. So maybe you had a case where dy dx is 2x plus y over x minus 3 or something like that. In those cases, remember that slope is rise over run. I don't want you to memorize this stuff when you get to this. If I wanted to know where this is vertical, it'd be vertical if I had rise but no run. So I would be looking for cases where I had a 0 in the denominator. If I wanted a horizontal tangent, I would be looking for cases where there is no rise but there is run, and I'd be looking for a 0 in the numerator. Right? Keep that in mind. Just an example. I know you've been taught well. Just to remind you, use the first derivative to justify. Just a max might be f. Keep in mind the subjects to the sentence, because there will be two subjects floating around there, f and f prime. F has a relative max at x equals c because f prime changes from positive to negative there. They used to say because x equals c is a critical number and f prime changes from positive to negative there. But they stripped it down to bare minimum and relative max at x equals c because f prime changes from positive to negative there. Don't use any pronouns. It means nothing. That could refer to f or f prime. And don't use the words the derivative. The derivative could be f. It could be f prime. It could be f double. The derivative doesn't cut it. Use symbols. All right? You get the idea on min. here we go. Use the second derivative to find concave. That's concave up is where f double is positive. Concave down is f double is negative. Inflection points. This is a very common error. Please write this down. It's where f double changes sign, not just equals 0. Yeah, you start by finding where f double is 0 or undefined, but then you do a sign test and you conclude, well, that the second derivative changes sign, not equals 0. All right? When you test for a min or max with the second derivative, rather than finding a flat spot and using the first derivative to say, hey, is it going negative to positive to see if it's increasing or decreasing? In the second derivative test, you don't test around, which is a huge benefit to it. You don't have to test regions, which is harder. You just test points. You first find where the critical numbers are. Find where the derivative is 0. Now, if it's undefined, the second derivative test will fail. So if you try to use the second derivative test at a sharp turn, it's not going to happen by the simple fact that if the first derivative doesn't exist there, well, how could the second derivative exist there? You can't take the derivative of something that didn't exist one level up. You know what I mean? So you're really only focusing on horizontal tangents in the second derivative test. You then test f double at that point to see if it's flat with concave up or flat with concave down. And your conclusion might look something like this. One example of the two. F has a relative, I'll go min, at x equals c because I need flat with concave up to have a min. So because f prime is 0 and f double is positive. Notice I'm not putting arguments on my f prime and f double. I'm okay if you do that too. It's the AP test also would not count off for that. Okay, so the second derivative test fails when either f prime is undefined because that critical number doesn't even exist, but also if f double is undefined or 0, then the test will also fail. Let's go with an example of that. If I said, hey, what about f of x equal x to the 4/3? The derivative is 4/3 x to the 1/3. You get a critical number at x equals 0, which is in the domain. F double is, what do we got there? 4/9 and x to the negative 2/3. That doesn't have a sign at the second derivative or at 0, and so the test would fail. What do you do then? You'd have to use the first derivative test. Now the second derivative is awesome and in fact has to be used when you're dealing with those non-function cases where the derivative depends on both x and y. You don't, if you got a derivative that was like 2 minus 3x over x plus y, you don't do some whack second, two-dimensional sign test. That's not a thing, okay? You can't test around the critical numbers. You want to test at, and that means the second derivative test, all right? So keep that in mind. All right. Curve sketching, if you use the fact that the first derivative tells you increasing or decreasing, and extrema, and the second derivative tells you concavity and inflection points, and you can get a really good curve sketch, plus knowing basics of pre-calculus like domain, shape of the graph like a cube or something like that, x-intercepts, y-intercepts. This used to be a huge, I mean, like half a test back in my olden days before graphing calculators. Now it's progressed to other stuff because you have a graphing calculator. This isn't as necessary. All right, that's all I had to hit. If you would get at your homework 4, this is 5, but that's not what I intend. Get out homework 4. Your homework is review 5. I will real quick go over answers. If you have questions, I prefer you can come up and, oh no, you can't come up. You can come up and touch the slides and send the video back, or you can preferably just talk to each other. Turn it in by the end of the period. And if you have questions on my key or just questions in general, we'll hit them tomorrow, okay? So if I go too fast, pause the video or just come up and rewind it a little bit. Review 4. Here we go, number 1. Y prime or dy dx is 1 plus 1 over x squared. 2. Y prime is 3 over 2 root x minus 4 over x squared. I got 5/3. The average rate of change, that is equal to, so notice that's a hard equal. If it says estimated derivative, then you're talking an approximation of slope at a point with slope between two endpoints. And AP, their College Board, does care that you show an approximation symbol not equal to. I got -9/2. C, I have 6. Another number 1, the second number 1. That sounds like me. I got 4 cosine alpha minus 3 secant squared alpha plus 5 secant alpha tangent alpha. 5, I'll check that myself just to make sure we're cool. 6, pay attention to notation here. I'm a little picky about my notation. Not picky, I demand that you show good calculus. When you have the derivative at a value, I should generally see 2 steps. One for the general derivative, 1 over x plus e to the x, and then another for the value going in, 1/3 plus e cubed. You might also use an evaluation bar. This is the general derivative saying, hey, I'm about to put in 3, and then I get 1/3. Each of those is okay because it shows the general, then shows the derivative, but never says anything untrue like this not okay mark. 7, y prime or dy dx is e to the x 2x plus whatever that says, x squared plus 3 e to the x. 8, you have to use a chain rule. I'll check that myself. 9, you have to use a quotient rule. It is the quantity tangent of x times 4x minus 2x squared over secant squared all over tangent squared. Low d high minus high d low over the square of what's below. Or over low low if you like. 10, you would need the quotient rule. I guess if you use the chain rule the way it is, then you'll have to use the quotient rule for the derivative of the inside. But a better way to do that would be to make your life easy. A good mathematician says, how do I make my life easy? And the best way to do this is before taking the derivative, rewrite that with a little log rule. Isn't log of a quotient equal to log of 1 minus log of x squared plus 3? Then you don't have that quotient rule, and boom, your derivative is easy peasy, -2x over x squared plus 3. Little old guy trick for you there, people. 11, I'll check myself. 12 is 1/2, it's product with chain. So 1/2 sine of x e to the x to the -1/2 for the derivative of the outside. The derivative of the inside is a product rule, sine of x e to the x plus e to the x cosine of x. That's just plugging in. I got 1,946.446. Hopefully you remember how to take a derivative with your calculator or approximate a derivative with your calculator. 14, f prime at 1. F prime at x is 1 over x, so f prime at 1 is 1 over 1. And the, what are we sketching here? Oh, I'm sorry. The sketch of log of absolute value of x allows positives and negatives. So you'd have a log and its mirror image because of the absolute value. Definition of the derivative, I tend to check. When I say use the definition of the derivative, yeah, I mean really use the definition of the derivative. And that means good notation, f prime at 2. You might have done either the definition with just generally and then plugged in 2, or you might have done 2. If you did 2, then it might look like this. F of 2 plus h minus f of h over h. Any which way you look at it, your algebra better be good, and you know what the answer is by power rule. Same deal on 16 and 17. Your work should look good. A tangent line to approximate. So first of all, establish what is the function. It's the square root function. Then establish a good point as close as you can to that question. 11, the closest square root, perfect square is 9, 3. Find the derivative to find the slope of the tangent line. I'm saying, here's my general derivative. At 9, the slope is 1/6. There's my tangent line. Y minus 3 equals 1/6 times x minus 9. Now I'm just plugging in 11 into my tangent line. And my estimate is 3 1/3. Okay? Notice this is hard equal because y of 11 indicates the tangent line, and it truly does equal. If you wrote the square root of 11, then you would be saying approximation is 3 to the 1/3. I am very picky about the correct notation there, so make sure you're paying attention to it too. Let's go. I have on whatever number that is, I don't even know, this problem, 3y minus cosine of x over 2y minus 3x. If every sign is opposite, then that also is fine. On the next one, you've got a product there in a chain. That's pretty gross. I said something like 3y cosine of xy over negative 3x cosine of xy plus e to the y at 1. So the problem is saying at x equal 1. Well, that's great, but this derivative depends on x and y. So I don't know if I intended for this to be this hard, but man, this was hard. I said, okay, well, I need the y. So the next thing I did is say, all right, well, if I go back to the original function, put in a 1 for x, then I need to solve this equation to find the y. I do that by intersection in my calculator. And once I find that, then I can plug it in. Now, if you got the derivative but then got stuck on that stuff, would you just write those notes to yourself? You don't need to go back and do it. I just want you, unless you want to, I just want you to know how you would have gone about that. That was a hard one, really hard one. All right, the other one I'll check just to see if you have a clue. Same deal, 22 should be easy. Analytically, not algebraically. You can't really do any algebra on that. The idea is you see that as a definition of the derivative of sine. You take the derivative, cosine of x, and realize it's at 2, so cosine of 2. Now, I might have got you on this bad boy because maybe you thought that was a typo, and it was not. This, you would expect it to be symmetric, and therefore this should be a 2. Now the question is, it's not a 2, so what do? Do you A, throw up your hands and say, I don't know, I quit, which is terrible, or B, you want it to be a 2, well, let's solve that problem. How could I make it a 2? Well, I could make it a 2 as long as I mathematically balanced it. Dividing by 2, multiplying by 2. Now, limit rules allow you, when you have a constant, to just do that out front. It's really about what the function does. The constant can be in front or inside or outside. And so really you can say make it 2 and balance with the 2. And so that means now it's a derivative. 2 times the derivative of 3x squared minus 1, which is 12x. If you got that one, then give yourself a little pat on the back. That's a humdinger. And boy, this one, I don't know if I covered this on Friday. I guess I will know today when I teach. Wow, when you prove a derivative doesn't exist at a point using a definition, it might look something like this. You should definitely use the alternate definition, is by far the easiest one to use. As you approach from the left, the function on the left uses 3 plus x. The slope from the left approaches 1. The derivative from the right uses x squared plus 3. The slope from the right is 2. Well, if one-sided limits are different, then the two-sided limit doesn't exist. If 1 is not equal to 2, the limit does not exist, and the derivative is the limit, and therefore the limit does not, the derivative does not exist. You might need to pause that and get a little, let that go through your little hamster wheel, and hopefully it went well. All right, once you're good, turn that in. If you need to rewind the video or whatnot, or talk it over with your math amigos, please do walk around. Miss Anna will just kind of supervise as you do your stuff. If you're done with review 4, then start working on review 5. Have a lovely day, and I will see you tomorrow.